All right, this video is going to be on the fundamental theorem of calculus. And there are two parts about the fundamental theorem of calculus that we're going to learn, and we're going to start with part 2. So before we get started with the fundamental theorem of calculus, we're going to remind ourselves what a definite integral is versus an indefinite integral. So a definite integral is the area under a curve. So whenever we found the area under a curve, we always had a boundary. We had a lower bound and an upper bound. So it has bounds. And so since it has bounds, it will give us a specific number that's the specific area underneath that part of the curve. And if you guys recall, whenever we find the area underneath the curve, it has to be continuous on the interval that we're using to find the area. All right, now an indefinite, well actually maybe let me write this. So this would be like we're looking for what the area is from A to B of f of x dx. All right, now an indefinite integral is an antiderivative. It will give us a family of functions. So this would look like the integral of f of x dx, and that is the antiderivative plus c. So here I'm not looking for a specified area underneath the curve. I'm just saying that all of these functions right here would have a derivative that's the same as this one, and it wouldn't matter what this constant number is at the end, that all of these have the same derivative. So it's a family of functions that just have different constants at the end. So the way I think of this in my head is a definite integral is defined, has two bounds. This is indefinite or undefined as far as the bounds go. So these are just general answers, and this is a more specific situation. All right, so now we're going to go ahead and move on to the fundamental theorem of calculus, part 2. And this is how we will evaluate integrals. So let's say we have a definite integral evaluated from A to B. Then that's going to be our antiderivative. And this is what we write when we evaluate something at different numbers. So I'm writing down that I'm evaluating at B and I'm evaluating at A. And the math that we do to do these evaluations is we take our antiderivative and we plug the b value in for the x's, and then we plug the a value in for the x's, and we subtract those two numbers from each other. So here are the examples for this. All of the examples are going to have the instructions just to evaluate. And when they have those instructions, we know, okay, we're doing the fundamental theorem of calculus, which means that we just have to plug these two numbers in. So if I'm evaluating the integral from 0 to 1 of x squared dx, then I know that I have to find the antiderivative of this. So we actually know that this answer is 1/3 because we've referenced this one before, but now we can see how we actually got 1/3 to be the exact answer. So not using rectangles to approximate it, not using trapezoids to approximate it, but the exact answer. We want to know where that came from. So here, I'm going to say I need to add 1 to my exponent, so that would be x to the 3rd, and then I'm dividing that by 3. And so my function there is going to be 1/3 x to the 3rd, and I am evaluating that at 1 and at 0, and I'm going to subtract those two things. So I have 1/3 times 1 to the 3rd power minus 1/3 times 0 to the 3rd power, and that leaves me with 1/3 times 1 to the 3rd is just 1/3 minus 0, and so that's 1/3. So that means that this definite integral, it's defined, so it's a definite integral, that the area underneath the curve from 0 to 1 is 1/3 exactly. All right, the next one is the integral from -2 to 1 of x cubed plus 1. And so the first thing we need to do is find the antiderivative. And so if I take that exponent and I add 1 to it, that would be 4, and then I'll divide this by 4, and then the 1 is a 1x. And so I've got 1/4 x to the 4th power plus x, and I'm going to evaluate that for 1 and for -2. And I'm running out of some space to write this. Well, so that's going to be 1/4 times 1 to the 4th power plus 1. That's my first number. And I'm going to be subtracting off 1/4 times -2 to the 4th minus -2. So if you type those in and you actually subtract that, you're going to find that the area underneath this curve would be -3/4. So the reason that the area underneath the curve is negative is because some of the pieces of that curve would have had a negative area or would have been underneath the x-axis. So that's why. All right, for our next example, let's say we are looking at integrating from -1 to 3 of 1 over x squared. And if you looked at this one, you would say that you could not integrate that because it's not continuous from -1 to 3. This graph has a discontinuity at 0, and that means we could not find the area underneath the curve from -1 to 3. So we're going to say that this does not exist because it is not continuous on the interval. All right, and our last of this type of example is to find the definite. We're doing the definite integral and we're evaluating it from 0 to pi-4ths. So if I think about what I must have taken the derivative of to get secant squared, I know that that would have been tangent, and I'm evaluating that at pi-4ths, and I'm evaluating that at 0. So I have to picture my unit circle. So 0 is right there, and that has a point of 1, 0. Pi-4ths is right here in the middle, and that is root 2 over 2, root 2 over 2. And tangent is, so I'm going to go ahead and write my work out for this. I'm going to say if I'm evaluating it from pi-4ths to 0, that would be tangent of pi-4ths minus tangent of 0. And tangent of pi-4ths is y divided by x, and these two numbers are exactly the same, so that means it's going to be 1. And tangent of 0, if we do y divided by x, that's just 0. So this is 1. So if I was to draw that curve, secant squared x, and shade the part from 0 to pi-4ths, the area of that would be exactly 1. Okay, so I want to compare this to 2 more examples. And these directions might just say to integrate. And so here, we are looking at an indefinite integral because I'm not defining the upper boundary and the lower boundary. So here, I am not looking for a specific area. I'm looking for a family of functions. So if I look at this one, for my first piece, I've got 10x to the 5th, and I added 1 to make it a 5, so I should divide by 5, minus 2, and then I have to picture what I would have taken the derivative of to give me an answer of secant squared, and that would have been tan x, and then I've got a plus c on there. And since I don't have a specific point to plug in to verify which specific function we were talking about, then I'm just going to say that our function is 2x to the 5th minus 2 tan x plus c, and I'll just leave it there. And then our last one is going to be, we're going to integrate cos theta over sine squared theta d theta. And this is one I wanted to look at because we've done some of these problems where we're finding the antiderivative, or in this case we're calling it integration. So we're essentially doing the same process. Here we're just using different notation for it. And I just want to make sure that we have seen all sorts of different types of problems with that. So when we're integrating this, or when we're finding the antiderivative of this one, this looks kind of like a quotient rule, but we have to remember that quotient rules is how you find a derivative. It's not how you undo a derivative. So to undo a derivative, we actually have to completely simplify this. So what I did to do that is I thought of this as cos theta over sine theta times 1 over sine theta. I kind of broke it up into two pieces. And then I said, well, cos theta over sine theta is actually cotangent theta. And 1 over sine theta is actually cosecant theta. So now I've fixed it, and you might not recognize that, or you might recognize it, but this, I'm going to go ahead and put d theta on the end of this. But this is actually the derivative of cosecant, or the negative version of this would be the derivative of cosecant. So this is actually the function negative cosecant theta plus c. So that's something to watch for when you're taking antiderivatives. There's no such thing as a product rule, there's no such thing as a quotient rule, there's no such thing as a chain rule when you're taking the antiderivative. You have to actually be able to take it back to something like this. That would have been one step to find it.